It looks like it's about time. Are you ready to get started?
Yeah, I am.
Awesome. Hi everyone. Welcome to this week's instance of the Pan Global Algebra and Logic Seminar. I would like to introduce Matt Evans, who's here today to talk to us about the spectra of BCK-algebras. So take it away, Matt.
Yeah, thank you. Well, thank you all for being here. And thank you to the organizers for the invitation to speak. Like Charlotte said, I'm going to talk about spectra of BCK algebras. And sort of, I kind of had this broken up into roughly four chunks, this talk. There's going to be some big picture kind of stuff at the beginning, which will be relatively brief. I'll give some reminders about, the definitions of BCK algebras and kind of the associated machinery that we need to develop. I'll talk about their spectra. And then at the end, I'll be closing with some conjectures about spectra for finite BCK algebras specifically. So in terms of the big picture, much of this sort of stems from work that I did for my dissertation. So I proved that the prime spectrum of any commutative BCK algebra is nearly, this is not a precise term, nearly a spectral space. Obviously I'll sort of, if you're not familiar with the terminology, I'll define it as we go along. But one of the big questions that I had at the time, or sort of shortly afterwards, was what happens if we drop the assumption that the algebraic structure has commutativity? And this was something that I worked on for a little while. And actually, I gave a talk at Blast, I think it was 2021, is what I've noted to myself here. But I eventually kind of put the project aside. And really, I mean, for almost 3 years, I hadn't really thought about it until maybe within the last 4 or 5 months. Something prompted me to start thinking about spectra specifically for finite BCK algebras. Some of the things that I'm going to talk about, I've actually already spoken about in a previous venue, and honestly had just sort of forgotten that this was something I had been working on. But in particular, some of the results, maybe really many of the results that I'm going to talk about today are contained in another paper in a much more general setting. This paper, Abstractly Constructed Prime Spectra, that appeared a couple of years ago. And I want to thank George Janelides for sending this to me, or at least calling my attention to this paper. Somehow, I really just hadn't seen this paper until quite recently. I mean, last week it was sent to me. I haven't, I would say, fully absorbed all of the results of this paper, but definitely, at a glance, a lot of the things I'm going to talk about today really sort of occur in a much more general setting. So I wanted to call attention to that. So what is a BCK algebra? The way I think of them is sort of purely algebraically. A BCK algebra is an algebra of type 2-0. So we have a binary operation and some distinguished element, which I'll denote by 0, that satisfies several equations and one quasi-equation. So I won't go through and read each of the equations here in detail, but there are in total 5 of them. So 4 equations and one quasi-equation. So the class of BCK algebras is a quasi-variety. It is not a variety, but it has lots of really interesting varieties, sub-varieties. And I'll talk about that in just a second. But really, I mean, there's a deep connection between algebras and logic here, right? BCK algebras are the algebraic semantics for a substructural logic, which we call BCK logic. And often in the literature, rather than using the binary operation of dot, you'll see an arrow instead, which is sort of the order dual to this. So instead of using 0 as the distinguished element, they'll use a 1. Really, the idea here is that the operation dot is meant to mimic implication. So this is a substructural logic that has only implication, although, again, from my perspective, it's sort of the order dual of implication. Now, these algebras are partially ordered. So we say that x is less than or equal to y if and only if x dot y equals 0. So if you look at equation 4, this tells us that 0 is the smallest element with respect to this partial order. So they're always bounded below. And so if I say a BCK algebra is bounded, that just means that it has a top element, which I'll generically call 1. So it has to satisfy this property that x dot 1 is always 0. For my purposes, I don't really care if I think of the element 1 as being in the signature or not. It's not tremendously relevant for what I'm talking about today. Oh, cat is saying hello. Okay, so we can define a term operation, which I'm going to say x meet y, but I want to be a little bit careful here. This operation is defined as y dot x. This element is always a lower bound for x and y, but in general, it might not be the greatest lower bound. However, when x meet y and y meet x are equal, then it turns out this element actually is greatest lower bound. And when this equation is satisfied for every pair x and y in the underlying set, then we call the algebra commutative. Commutative BCK algebras have a lot of interesting properties. This class of algebras is a variety, so you can write down, an equational basis. And most of my work over the last few years has dealt specifically with commutative BCK algebras. And one thing that's been known for a long time is that a BCK algebra is commutative if and only if it is a semilattice with respect to this term operation of meet. But certainly it can happen that the underlying poset of A is a semilattice, but perhaps not with respect to this operation. That is a thing that can happen. So even when the algebra is not commutative, the underlying poset might be a lower semilattice. And in this case, I'm going to refer to such algebras as BCK semilattices. So I have a series of examples here. Any Boolean algebra is a bounded commutative BCK algebra with the operation defined by x meet the negation of y. Which, sort of as a special case, if you just take any power set together with set difference as your operation, right? That gives an example of this. If we take, say, the non-negative reals with respect to this kind of truncated maximum, right? So the max between x minus y and 0, that turns, this gives a commutative BCK structure, though clearly it's not bounded. And more generally, here again, there's a class of examples. This is just one of many. If you take any abelian lattice-ordered group and you take its positive cone, that will also have a commutative BCK structure on it. And there's some, particularly nice subalgebras of this one. So if I take the natural numbers together with 0, this gives me a subalgebra. Or if I take any finite chain, I can view as a subalgebra of this particular algebra. So this algebra has lots of nice kind of examples sitting inside of it. Another class of examples, if you take any set and any BCK algebra A, you can look at sort of a function algebra. So the set of all functions from X to A with a pointwise defined operation. Because the operation is defined pointwise, this algebra sort of inherits the structure of A. So if A is commutative, so is this algebra, and so on and so forth. A couple more examples. So I thought it would be interesting to include an example of something that's not commutative, but the underlying poset is nice. So in fact, this is a non-commutative BCK algebra, but the underlying poset is actually a lattice. So you just take the natural numbers with 0 together with this operation. So if x is less than y, you output 0. If x is greater than y and y is not 0, you output 1. Otherwise, you output x. In this example, the underlying poset is just the natural numbers. I mean, it's the same partial order as the natural order on the natural numbers. And then finally, I'll just observe that not all BCK algebras are BCK semilattices. So smallest example has order 5. I didn't write down the operation. I just wrote down the partially ordered set, but this is not a lower semilattice. So, the class of BCK semilattices is larger than the class of commutative BCK algebras. Okay, so given a BCK algebra, we'll say a subset I is an ideal if it contains 0 and if it satisfies this kind of, I like to think of this as like a backwards, quote unquote, backwards modus ponens. So if x dot y is in the ideal and y is in the ideal, then x is in the ideal. And going forward, I'm just going to let ID of A denote the lattice of ideals of A. And there are going to be, sort of 2 or 3 different types of ideals I'm going to be interested in. So I'm going to say an ideal is irreducible if it is meet irreducible as an element of the lattice ID of A. I'll say an ideal is meet prime if it's meet prime as an element of the ideal lattice. And then finally, if A is a BCK semilattice, we'll define a proper ideal to be prime if whenever it contains the greatest lower bound of x and y, that implies that it contains either x or y. This is sort of I think, a relatively standard definition. But I did want to point out specifically in the case that A is commutative, right? This property looks like maybe the more obvious property, right? X meet y contained in P implies that X is in P or Y is in P. So it's been known for a while. This was proven by Pawłowski in 81 that in a BCK semilattice, there's an equivalence between the irreducible ideals, the meet prime ideals, and the prime ideals. But in fact, we can say something a little bit more precise because as it turns out, the ideal lattice is always distributive. This was also proven by Pawłowski in 81, though in a different paper. The ideal lattice is always distributive. So in fact, irreducible and meet prime ideals always coincide for any BCK algebra. So we actually don't need our algebra to be a semilattice for 1 and 2 to be equivalent. And irreducible ideals are really the ones I'm going to care about going forward. So I'm going to let x of A denote the set of irreducible ideals of A. So for example, when your algebra A is commutative, this is just the set of prime ideals. But I'm sort of trying to generalize things that are known about the prime spectrum. So we'll focus on the irreducible ideals. And this is the set that we will topologize in order to obtain the spectrum. So given a subset S, I'm going to define sigma of S to be the set of irreducible ideals that do not contain S. This is a relatively standard construction for algebraic structures. And just notationally, instead of writing sigma of the singleton set A, I'll just write sigma of A for simplicity. So 2 things that we can prove without too much trouble is that if I take sigma of I indexed over the ideals of A, that family becomes a topology on the set of irreducible ideals. And in particular, we can take sigma of A ranging over the elements of the algebra to be a basis for this topology. So this topological space, this is what we refer to spectrum. Now, one thing I do want to mention here about this particular proposition, so to the best of my knowledge, this was first at least published, maybe it was known before this, but at least first written down in the literature in 92. This is a result of Aslam, Diba, and Fahim, but they were specifically working with commutative BCK algebras. So in their proof, they're assuming that the algebra is commutative, but if you sort of go through very closely and do a very close reading, you realize that they're not actually using the fact that they're working with prime ideals in the sense of a commutative BCK algebra. What they're really using is the fact that prime ideals happen to also be meet prime elements of the ideal lattice. So in fact, this proposition is still true even if the algebra A is not commutative, because all we're using is the fact that we're looking at meet prime ideals. Or I guess here, we're using irreducible ideals, but of course, again, irreducible and meet prime ideals coincide for BCK algebras. So we have a topology, okay, and it works even when the algebra is not commutative. And there's a strong connection here with what are called spectral spaces. So a spectral space is a topological space that is homeomorphic to the prime spectrum of some commutative ring. But there's also a really nice way of characterizing spectral spaces. So in the late 60s, Melvin Hochster, in his PhD thesis, actually gave a characterization for spectral spaces sort of purely topologically. So a topological space is spectral if and only if it satisfies, well, I'm going to write down 4 properties, but really there's some redundancy in the definition I'm using here. It's really 3 properties. Anyway, what we need is that the space is compact. The space needs to be T0. The collection of compact open subsets is a basis that is closed under finite intersections. And the space should be sober, meaning that every irreducible closed subset is the closure of a unique point. So like I say, there's a little bit of redundancy in this definition because being sober implies T0. So maybe a more accurate way of saying this is that X is T0 and X is quasi-sober, which is that every irreducible closed subset is the closure of some point, and then T0 would force uniqueness. I'm following this definition because there are various sources in the literature that include all 4 properties. So for the sake of simplicity, I'm just following those references. And how does this relate to BCK algebras? Well, in the late 90s, Meng and Jun proved that if you have a bounded commutative BCK algebra, then the spectrum is actually a spectral space. So it satisfies these 4 properties. And so when I was in graduate school, this was sort of where I picked up the story. Knowing this result, my kind of motivating question is, well, what happens if we drop the assumption of boundedness, just as kind of a starting point? What can we say if the algebra is not bounded? Right, so I'm going to keep the assumption of commutativity, but weaken the assumption of boundedness. So in their proof, they use the fact that the algebra is bounded to obtain that the space is compact, which is certainly sufficient, but definitely not a necessary condition. Because, for example, if you just take any BCK algebra with finitely many ideals, well, if it has finitely many ideals, then the spectrum has finitely many points, and any finite topological space is necessarily a spectral space. Or in this case, I mean specifically compact. So finite space must be compact. So this led to sort of one of my first results, that if you have a commutative but not necessarily bounded BCK algebra, then many of the same properties characterizing spectral spaces are still true, with one exception. So the first is that the spectrum may not be compact anymore, but it will always be locally compact. It's still T0. The compact open subsets still form a basis, which is still closed under finite intersections, and the space is still sober. In the literature, any topological space that satisfies properties 2, 3, and 4, so something that's not quite a spectral space, where the only thing missing is compactness, those are referred to as generalized spectral spaces. So the spectrum of any commutative BCK algebra is a locally compact generalized spectral space. Or sometimes I've also seen the term schematic space applied to this, but I've seen generalized spectral space more frequently. So I think, this is a relatively nice result. It's not tremendously difficult to prove. But of course, sort of a natural follow-up question is, well, what can we say if we don't have commutativity? Like, how far can we generalize this result? I'm getting a little bit ahead of myself, sorry. Another thing that I proved shortly afterward is that we have compactness, meaning so the spectrum is compact and therefore spectral, if and only if the algebra is finitely generated as an ideal. And here again, I did something similar to something else I talked about earlier, which is I just went through the proof and, sort of with a very fine-tooth comb, I looked at where am I using the assumption of commutativity for this compactness result, right? Where is commutativity being used? And it turns out, well, I'm really not using commutativity. If you go through the proof very carefully, you realize that if you just replace every instance of prime ideal with irreducible ideal, the proof goes through otherwise unchanged. So I guess what I'm saying here is I was never really using the fact that the algebra was commutative. What I was using is the fact that in a commutative BCK algebra, prime ideals are irreducible ideals. So if I instead focus my attention only on irreducible ideals for a general BCK algebra, then the same result should be true. And like I mentioned before, this kind of prompts some further questions, right? What other things can we say? What results still work if we're no longer assuming that the algebra in question is commutative? Now, in order to do this, there's some kind of like foundational things that you need to go back and check still work. For example, one thing that we need to know is that the basic open sets, the sigma of A, are compact. In a lot of my previous work, typically what I would do is I would just cite the proof by Meng and Jun, where they proved that a bounded commutative BCK algebra has a spectral spectrum, that the spectrum is a spectral space. So I would just cite this particular result. So you do have some work to do here. You have to go back and actually prove that these sets are compact, even if the algebra is not commutative. You can't rely on this previous result. And it turns out that proving this is relatively straightforward. So I'm going to show a quick proof. I actually think there is a much easier proof than the one I'm going to present, but this was sort of the first proof that I wrote down, that for each A in your algebra, for every element of your algebra, the set sigma of A is compact and open. Okay, so I'll let sigma of I lambda be some open cover. Right, so this means that sigma of A, right, is a subset of the union of all these open sets. Now, there are some properties of this map sigma. I'm not going to go through the proofs, but if you're willing to believe me here, The way that sigma behaves with respect to unions is that it turns unions into joins. So really what we're saying is that sigma of A is a subset of sigma of the join of all the I lambdas. And then as it turns out, this map sigma, it's not just order preserving, but it's also order reflecting. So we actually have that the element A must be an element of the join of these ideals. And just by some like general kind of BCK theory, there's a really nice characterization of when an element is contained in an ideal. So this element A, to be contained in the join of these I lambdas, what that tells me is that there has to be a finite list of elements, B1 through Bn, contained in the union of the I lambdas that have this product that, A dot B1 dot B2, et cetera, up to B sub n, that product has to be 0. But of course, that tells me that I'm really only using finitely many elements, right? So the element A is really contained in the join of finitely many of these ideals. So let's say, B sub I is contained in I sub lambda I, right? A is in the join of this finite list of ideals. And so sigma of A gets covered by this, finite collection of open sets coming from our open cover. And, again, I think the important thing to emphasize here is I'm not using commutativity of the algebra in any significant way. Unlike the proof by Meng and Jun from the late 90s. That proof does use commutativity. Okay, so, again, I sort of went through a list of all my previous results, and I just asked, what can we say if the algebra is not commutative? And several of the proofs really don't rely on commutativity in any significant way. For example, the spectrum is still locally compact. The compact open sets still form a basis. And the spectrum, is still sober. The first of these two are really straightforward. I mean, the proofs are relatively short. The third proof does require maybe a little bit more work. It's not quite as obvious how we can do this without commutativity, or it's maybe not clear that commutativity is never being used. But sort of the key ingredients for the spectrum being sober, one is that the map sigma needs to be injective, which you can prove without commutativity. It's important that the spectrum consists now of irreducible ideals. So I'm not referring to prime ideals because I don't have commutativity, but I do use the sort of irreducible property. That is a thing that gets used in the proof, so we need that. And we need to know that every ideal is the intersection of the irreducible ideals that contain it. And here again, I mean, this is a result that was proven sort of several times over, I would say, in the literature, but under a variety of different hypotheses. So sometimes, you would see proofs that require commutativity, but there is at least one proof that does not require commutativity. So we get that the spectrum is sober, locally compact, and that the compact opens form a basis. But you might notice that there is a sort of critical thing missing. One of the properties that we needed in order to be a spectral space, let's say, is that the compact opens not only form a basis, but are also closed under finite intersection. And that is a little bit trickier. So you can sort of ask, what can we say about the closure of compact opens under finite intersections? Okay, well, let's suppose we have two compact opens. By sort of our general setup, we can write the intersection as this kind of double union, right? So I guess, each of U and V can be written as a finite union of basic open sets. So sigma of AI, sigma of BK. And, what you really want is that each of these intersections, right? The sigma of AI intersected with sigma of B sub K, you would like for that itself to be a compact set. I mean, certainly an open set, so you want it to be compact. So under certain hypotheses, this is guaranteed. For example, If your underlying algebra is commutative, then the intersection of sigma AI and sigma BK is just exactly sigma of AI meet BK, which is sort of, I mean, that not too hard to convince yourself that should be true. We can weaken that a little bit. If the underlying algebra is a BCK semilattice, well, then we no longer have a semilattice structure with respect to the operation of meet, but we can just take the greatest lower bound. There's a little bit of work you have to do here, but it turns out a similar statement is true that, sigma AI intersected with sigma BK is the same as sigma of their greatest lower bound. So at the very least, we can say that if the algebra is a BCK semilattice, so this is now a wider class of algebras than just the commutative ones. If your algebra is a BCK semilattice, then the spectrum is a locally compact generalized spectral space. And we know we have compactness, or we know that the spectrum is spectral if and only if A is finitely generated as an ideal. All of these things still work, even if we weaken commutativity to just being a lower semilattice. But of course, like in general, the intersection of two compact open subsets doesn't have to be compact. In general, these spaces are not Hausdorff. So, you have to be a little bit careful here. But certainly, any open set of the form sigma of I is compact if and only if I is finitely generated as an ideal. So, I guess sort of the general question would be, when can we characterize when the intersection of two compact open subsets is compact? That's really equivalent to asking, like, what are some conditions on the underlying algebra that guarantee that the intersection of finitely generated ideals is itself, that the intersection of two finitely generated ideals is itself finitely generated. And I think this is a question that has received some attention, maybe not specifically for BCK algebras, but sort of in general, right? When is the intersection of two finitely generated substructures itself a finitely generated substructure? I'm not tremendously familiar with the literature in this kind of line of reasoning, but I do believe this is a thing that has been studied. So for me, specifically with BCK algebras, I would love to have some kind of characterization here. But one way we can sort of simplify our lives, or at least maybe gain a little bit of traction on this, is well, let's assume that A only has finitely many ideals, right? This problem sort of, well, I should be a little bit careful. What I really mean, what I should really have said here is when A, the underlying algebra, is finite, this problem resolves itself, because certainly any ideal in a finite BCK algebra will be finitely generated. The intersection will be finitely generated, right? There's no issue here when the underlying algebra is finite. But in fact, also, of course, if the underlying algebra is finite, then the spectrum is a finite space and already spectral. We already know that. So very recently, what I've been looking at is specifically finite BCK algebras and looking at what can we say about the different spectral spaces that occur as the spectra of finite BCK algebras. So Meng and Jun, they had a book that was published in the mid-90s about BCK algebras, and in an appendix, there's just a list of all BCK algebras up to order 5, which includes, a breakdown of their ideal lattices. It's very nice. And it made it very easy to just sort of sit down with this finite list and write down, okay, here are all of the spectra that occur for these finite BCK algebras. And so what I've put together here is just some kind of statistics, a kind of general breakdown of the data that I collated based on the order of the algebra. So if the underlying algebra has order 2, well, there is a unique BCK algebra of order 2. It is a simple algebra, so its spectrum is a one-point space. There's not much of interest happening there. Similarly, when the underlying algebra has order 3, the spectra that occur, well, there's one simple BCK algebra, so it's a one-point space, and then you have two that are not simple. Both of them have two-point spectra, one of which is the discrete space on two elements, the other is the Sierpinski space. And you sort of just continue doing a bunch of computations here. So for order 4, there are 3 one-point spaces. Well, I should be clear here. I'm just tabulating the numbers. So I'm not necessarily saying these are not homeomorphic. I mean, one-point spaces are all homeomorphic. Anyway, you have 3 one-point spaces that occur. There are 6 spaces that have an underlying 2-point set, and then 5 that are 3-point spaces. The spectrum is a 3-point space, and so on. So for order 5, you get 14, 28 spaces with 2 points, 30 spaces with 3 points, and then 16 spaces on 4 points. And this is really, unless you do a lot more work, this is kind of as far as you can go. As it turns out, for order 6, there are 775 different non-isomorphic BCK algebras. So really, that is not tractable to do by hand unless you just have a lot of free time. And so I guess, this is not a lot of data. There's not much to sort of pull from here. I think there are some patterns that are perhaps a little bit suggestive, but there's one particular thing I want to take note of. So I guess the one pattern I kind of want to call attention to is the main diagonal, 1, 2, 5, and 16. To me, this is the most interesting. In each of these, the indicated boxes really, they represent non-homeomorphic spaces. So for example, for BCK algebras of order 5, there are 16 of them that have a 4-point spectrum, and all 16 of them are non-homeomorphic. The reason, whoops, went a little too fast there. So the reason I think this is significant is because these numbers are exactly the number of non-homeomorphic spectral topologies on a 1-element, 2-element, 3-element, and 4-element set, respectively. So for each order, it appears as if we obtain every possible spectral space whose with an underlying set that is one less element. Or maybe to be a little bit more precise, my general conjecture here is that for every spectral space on n-1 elements, there is a BCK algebra of order n whose spectrum is homeomorphic to that spectral space Y that you started with. I've done a little bit of work in this direction. I don't have anything concrete yet, but I believe this to be true. But we can also maybe approach this problem a little bit differently. One thing that is known is that there is this dual equivalence between the category of spectral spaces and the category of bounded distributive lattices. So given a bounded distributive lattice, if you take its prime spectrum, you get a spectral space. Conversely, if you have a spectral space and you look at the compact open subsets, that always forms a bounded distributive lattice. And that's a dual equivalence. So you can sort of, so one thing that is known is that if the spectrum is a Noetherian topological space, meaning it satisfies the descending chain condition on closed subsets, then the lattice of compact open subsets is actually isomorphic to the ideal lattice of the underlying algebra A. And certainly in this case, if you're focusing your attention on finite BCK algebras, well, every finite topological space is Noetherian. Or excuse me, uh, we know that the spectrum is spectral and therefore Noetherian. Let me say it that way. So you can ask, or you can sort of make the conjecture that every finite bounded distributive lattice occurs as the ideal lattice of some finite BCK algebra. And here again, this is a thing that I believe to be true, but as of yet have not come up with a nice proof. Okay, I think I went a little bit fast, but that is actually everything that I wanted to say. And I've got my list of references here at the end. So thank you for your time and attention.